Hi and welcome to our video on sketching graphs using what we know so far. So I haven't really prepared much for this. Here I've got a function. It's a bit of a complex function. It's not too bad. There's not a lot of constants floating around in it. But it is a linear function multiplied by an exponential function. So we're going to sketch this function. Now there's a little interesting point I want to make first, and that is that if I sketch those two functions, let's say we split up and we sketched in green, first of all, 2x. So obviously 2x would be, oh, I've missed. Let's just pretend I didn't miss. See that pen there? I didn't miss it. So that's why y equals 2x. It should go through the origin. And my second function is e to the negative x. Now, e to the negative x, obviously it's an exponential function, but x is negative. So it kind of looks like this. Yeah, and that blue's not really worked all that well. There we go, that's better. So there's my e to the negative x, and I'll just write that down here, y equals e to the negative x, and of course I probably should pop a nice little yellow label on here, y and x. Now we can explore this. Before we even start doing this question, we can explore this and go, well, what happens actually when I multiply 2x and e to the negative x? Let's have a look. So here, 2x is quite big, e to the negative x is quite small. I don't really know what's going to happen there. That'll be an interesting result. Over here though, e to the x gets really large. We actually know that e to the x or e to the negative x gets larger a lot quicker than that linear function will. So this is going to get massive. This is actually going to get pretty big as well, but that's negative. And that is positive. A negative times a positive, it's going to be right down here, and it's going to be huge. And as we go along, it's going to go to infinity. So we're just getting a bit of an idea here. Somewhere in here, we're probably going to end up with a 1. So that's going to be positive and probably huge positive. Oh no, well actually, so this exponential is probably going to outweigh this linear, so it's probably going to come up, do a bit of that. Anyway, we've got a bit of play with it. But let's determine everything we can, and then we'll start sketching those important points. So the first thing to determine is y and x intercepts. So we'll do this as number 1, y intercepts and x intercept. Now y intercepts occur when x equals 0, x intercepts occur when y equals 0. So we can start with that and determine these. So when x equals 0, I get y is equal to 2 times 0 e to the negative 0. Now what's e to the negative 0? Who cares? 2 times 0, the whole thing's 0. So y-intercept occurs at 0 when x is 0. So we've got this coordinate, 0, 0. So that's important. Secondly, the x-intercept is when y equals 0. And so we're going to substitute y equals 0 into our function here. I get 0 equals 2x e to the negative x, and I need to solve that. Now, you've done this type of thing before, and in a sense, because you've done the null factor theorem in quadratics. So we're going to talk about the null factor theorem here. I've got 3 things multiplied together essentially, but the 2 doesn't really matter. So I'm going to separate it about here, put a little comma there. 2x times e to the negative x. For that to equal 0, one of those 2 things must be 0. So either 2x equals 0, which gives x equals 0. That's one solution. Or e to the negative x equals 0. And e to the negative x equals 0. I can turn it into a log, I can play around with it, whatever. Ultimately, you can't do it. It doesn't happen. So here, have a look at my blue line here. There's e to the negative x. And it never gets to 0. It gets really small, but it never gets to 0. So that can't happen. So we've got one solution there, which gives us this coordinate, 0, 0, which is a coordinate we already have. So it only crosses the x and y intercepts once each, and it's at the same point, 0, 0, which I'll probably fail to hit because I did there, but anyway, we'll get to that. So there's my first thing. Secondly, we can find stationary points. So these are our SPs. To find the stationary points, I need to go through and find where the derivative equals 0. So I want to let dy dx equals 0 to find my stationary point, and to do that I need to calculate dy dx. So let's start with this. Y equals 2x e to the negative x. To derive this function I'm going to let u, that's a y, sorry, there's a u equal 2x and v equal e to the negative x, because this is a product rule question. So make sure that you can identify that. So u equals 2x, which means that u dash is equal to 2, v dash is equal to negative e to the negative x, and then product rule means I get this little cross in the middle. I get y dash, or dy dx, is equal to 2 times e to the negative x, 2e to the negative x, that's my u dash v, plus v dash u, which is 2x times negative e to the negative x, so it's negative 2x to the negative x, and this is equal to 2e to the negative x minus 2x e to the negative x. And of course I can factorise that, and I always should if I got the chance. 2e to the negative x outside of 1 minus x. There we go. Now I want to know what happens when dy dx equals 0, and I'm going to quickly run out of space, and I'll probably need this for some work later on. So what I'm going to do is do something really cheeky and poorly worked, pretend I didn't run out of space and just finish it off here. So I get, when does dy dx equal 0? 2e to the negative x times 1 minus x equals 0. When does that happen? Well, let's solve this. I've got null factor theorem again. Either 2e to the negative x equals 0, which doesn't happen, or 1 minus x equals 0 and x equals 1. And of course, I do need to determine what is the value when x equals 1. So it's my value of y. So at x equals 1, y is equal to 2 times 1 times e to the negative 1, and that just becomes 2 over e. That's a poorly written e. Let's try that again. E, that'll do. And so we get this point, 1 comma 2 over e. And because I've worked that so badly, let me just recap on it very quickly. Y-intercept, x-intercept, x equals 0, y equals 0. Stationary points when dy dx equals 0, and they occur, I derive it first, I had to do some product rule stuff, and then I let that equal 0 and solve, and the null factor theorem came back into that again. I've got one stationary point at 1 comma 2e. Now the other thing I need to do is check to see if that's a minimum or a maximum. That's going to be important as well. So what I'm going to do is, I'll just quickly do that over here. I'll stick with blue, but my d squared x dy squared, in this case, so that thing derived again, turns out that it's, and you can do this yourself if you want to, but when I do u dash is just 2e to the negative x times that, I get 2e to the negative x times 1 minus x, and then v dash is just negative 1, so I get minus 2e to the negative x, and of course when I simplify that I get 2e to the negative x times 1 minus x minus 1, and that becomes negative 2 x e to the negative x, and at x equals 1, d squared x dy squared will be equal to negative 2 times 1 times e to the negative 1, which is just negative 2 over e, which is excellent. We don't care about the 2 over e bit, it's negative, and therefore it's a maximum. That's all we care about there. Okay, so I've just rubbed this out, and I'm going to sketch what I know onto a set of axes, but I'm just going to make that set of axes a little bit bigger here, and use some of the knowledge that I have about where this is going to head. Obviously you'll have a little bit more space, and you'll use your space well. If you're writing this out, that's going to really go in one line better. I do know this, I know it goes through there, 0, comma 0, and I also know it goes through 1, comma 2 over e, so 1, comma 2 over e. 2 over e is about 2.718, so that means that this is slightly less than 1, so my actual 1 value is about there, and obviously, I didn't actually mark the position, but let's put it here. Let's roll this out, let's put it there, and put 1 there. Okay, so that's my point there, because I know where this is going to head. Now what we're going to do is, we know that's a maximum, so we know it sort of does this, and it goes like that. But we're going to do one last thing. We're going to investigate what happens as x gets really large and x gets really small. This should give us the rest of the trends. Nothing else happens here. We know there's no other x or y-intercepts. We know there's no other stationary points. So now we're just looking at, well, what happens as we travel on. So if, let's say, for example, x was 100. 2 times 100 is 200. E to the negative 100 is 200 over e to the power of 100. Now, 2.718 to the power of 100, you put that in your calculator, it's probably going to come back with an error and not work. So just keep that in mind. basically we put in the crazy number up here and we get 200 divided by something massive, which means we're going to get something really small. And that means that this does this. It comes down here and just floats them on in there. And if we try a negative number, 2 times negative 100, so again I'm just picking a crazy large number, putting in the calculator, e to the power of negative 100 is e to the power of 100. E to the power of 100 is massive. Negative 200 is also pretty big, so that's going to be a huge number, but it's a negative times a positive, so it's going to be a hugely negative number, which means that this now does this. And that's our function. So it comes from negative infinity, passes through 0, 0, reaches the maximum now and carries on here. And how did I find that function? I just explored, first of all, x and y intercept, that's always my starting point. Secondly, stationary points, if there are some, there is, that's good. I've got most of the knowledge there already. I know that this stays here because it doesn't cross the x or the y axis again from here. So then I just explore a large number to see what happens as we go to infinity, there it is. And I explore a large number down here to see what happens as we go to negative infinity, there it is. There's a pretty good sketch of my graph. The only other thing I could explore is that there was a special point in here called a point of inflection. And a point of inflection occurs when d squared, I've done it upside down, haven't I? D squared y dx squared equals 0. That thing there should be d squared y dx squared as well. I apologise about that. When that's equal to 0, we get a point of inflection, and that's where the rate of change has got like that turning point. So it's curling that way, and then it starts to curl this way. That's what a point of inflection is. But we'll see that in another video. Anyway, there's a sketch of this graph. It's a pretty tricky function, but the maths isn't too bad because it's a fairly simple product rule. But this is abstract. But you can test those points. So it's always, in summary, y and x intercept, stationary points when dy dx equals 0, possibly points of inflection, which you can explore later on, and then just have a look at the things you don't know. Usually, what happens as we get to the really large numbers, what happens as we get to the really large negative numbers, and that will give you the trend that you can use. Thanks for coming. Hope you enjoyed it.